Hello again, everyone. This is an interesting topic. Maybe I'll start where Lucio left off, with actually something Patrick said as well. You know, when we're talking about trying to do things fast and innovate, you have to look at what you're doing now versus what you might be doing when we have a commercial, first commercial prototype. They are going to be different things. You need to be able to regulate with enough of a sandbox to play in, because we don't know what the machine's going to look like. We've got a variety of different approaches to fusion. We've seen that from Susanna. Doing the inertial approach, you see tokamaks, stellarators, and some other more exotic concepts. They're all going to be quite different, so you can't have a one-size-fits-all, this is how we're going to regulate from day one. My opinion is that ITER made a mistake by going down the nuclear regulatory pathway. That set a very, very high bar to meet very early on. And I think, to be clear, and this has been said a few times, I'm asserting my opinion here, regulation is the public's guarantee that fusion plants will protect people and the environment. So that's what it's there for. No one's saying let's not be safe. We're saying let's start from here and build up on top. And in fact, I've talked to a few people about communication over the last 24 hours. We're here to inform and educate from the fusion side those in communities that have connections and knowledge of the other areas in financial markets, in politics, in policy. When you communicate, you start with something simple and then you add complexity on top. You don't do it the other way around. You don't dive into the deep end and go, right, here's the really complex stuff, and let's pare it back, to your point, Patrick. So anyway, that's some initial thoughts. Fusion's not fission, but the core philosophy, you know, these are fundamentally both nuclear technologies. I always say this. I'm a nuclear engineer by training, and therefore I have studied ALARA, how we do things in the fission industry. And I don't think we need to apply that in the same way, but we do need to be aware that this will have radiological hazards. Now, fusion does have a lower hazard profile. There's no long-lived waste, potentially. That is a conditional statement, by the way. If you ask me today the best materials we have, it would. Small quantities, small concentrations of isotopes inside materials will result in long-lived waste. Full stop. However, there are routes that we can pursue that will end up with that not being the case. So we have to find those. And there's certainly no meltdown scenario, as there can be with fission. So it is a different thing. So the depth of defense can be lighter, but I think the discipline has to be rigorous. Layered protection, not one silver bullet. So what I mean by that is fusion plants can rely on barriers from engineering, procedural, operational, and cultural, safety culture, to prevent accidents. But regulators should judge the adequacy on each layer rather than one prescriptive design. So again, we've already had this point. I think one thing, and I'll move on to another topic, so I think Bank Inter wanted me to speak about the UK and what the UK is doing in regulation, so I'll speak for that in a second. But one final thing as a general comment is regulation is also an enabler of public trust. You've got one shot at this. If you get it wrong, you lose public trust, you lose your social license. It's very hard to get that back. When you lose trust, building it back is impossible. Okay, so the UK. So I'll talk a little bit more objectively about what the UK is doing. So this is really just for information. The UK, as we heard earlier, does have a pro-fusion regulatory model. It tried to be world first, and it moved very fast to begin with, and then the US kind of overtook when it made the decision in 2023. But the Energy Act in 2023 confirmed that fusion is not subject to nuclear site licensing. The government decided to shift the regulatory responsibility in the meantime, so for now, for where we are today, to the Health and Safety Executive and the Environment Agency. So these are two regulators that exist in the UK and govern a bunch of things, and what they're being told now is you are responsible for anyone developing fusion stuff. And what they're doing is they're speaking to the Office for Nuclear Regulation, they're speaking to other regulators, fusion experts, the UK Atomic Energy Authority, and AWE, for example, the weapons establishment, to work out what they need to do in terms of regulation. So again, starting from that point and building on top. They want to adopt a risk-proportionate technology agnostic approach again, so trying to get towards something. The UK does have a national program, something called the STEP device. If you Google STEP fusion in the UK, that's what's coming next for the UK. It's a really unfortunately named device, because when you say the next step for STEP, there's a lot of those in fusion, I think. So it wants to use STEP to help regulators work out in real time. STEP's under conceptual design at the moment. It's moving towards engineering design in the next couple of years, maybe in the next 12 months, in fact. Through that process of development and design, they will work out what do we do with handling materials, how are we dealing with tritium, which I'll come to in a second because it's the topic I'm going to speak about next, remote maintenance and so on. And they want to learn those lessons through that in silico process, through that design process, before they actually have any kind of things being built. built. And that will be supported by test rigs, Liberty, for example. These are going to inform and provide data points on the path. It wants to have an ability to license a fleet of reactors. That's how we want to get to. That's where we want to get to in the longer term. And the UK's sort of wants to bring players to the UK market to say this is the place to do it. We have a positive innovation environment from a regulatory standpoint. That's the UK government's main mantra at the moment, and that's particularly the case because it wants investment into the UK. So it says, come here and build, and we'll help you do it, not put barriers up. And I think, by the way, we talked about Europe, to be quite blunt, Europe's going to struggle in that regard. You could be talking about a brain drain of talent from Europe to places like the UK, happy for me, sorry, where you're saying, well, actually, I can go and I can do something more exciting. I can work faster. So Europe, I think, can catch up, and I hope it does. So that's the competitive advantage. Okay, so I'm going to spend just a few minutes talking about something particular that my current company works on, and also what I sort of study and have studied is tritium. So tritium is going to be the main thing that we have to work out how to manage. This is regulating the fuel of the future. Okay, full stop. This is the fuel of the future. It's something we know how to manage. It's radioactive. It's a 12.3-year half-life, which, for those who don't understand what that means, that's not actually a big deal. 12.3 years is a very long time, and it's a very low-energy beta emitter. Now, Patrick, your vial, nothing's coming out of there. You can hold tritium in your hand. It can't even go through the radiation won't even go through the skin. You ingest it, you inhale it. That's a different story. So you do have to be serious when it comes to safety about this. But it is manageable. You can manage this inventory of tritium safely. So it's extremely mobile, and that's one of the key differences between fusion and fission. Fission, you have your fuel in a stack. It's in solid form or salt form in some designs, and it's there. In fusion, your inventory is everywhere. It's a gas. It's mobile. It moves through all materials. It gets everywhere. It's hydrogen, so it's sticky to everything. That means we have to manage where it is in the machine, where it is in the plant. So monitoring, containment, detritiation, so taking things out of the materials where it gets stuck. These are all problems that are technical in nature, operational in nature, and will have a safety implication. So how do you regulate to ensure that you're knowing where your tritium is at what time? So accountancy at the sort of gram level is going to be needed, and that goes for external to the plant as well. So off-site releases, transfer of tritium. This will become the thing that we're powering the world with. So it's going to be the new thing. Waste pathways, emergency planning. What level of regulation is going to be required for those? And as we've discussed before, and I can chat about this in more detail, dual use. Tritium is an export-controlled isotope. There are a number of other things in fusion that are export-controlled. We are dealing with this today. We are using tritium. I think EXIM are not yet using tritium, but Commonwealth Fusion Systems are. It's a known entity. It's not something that we've never done before, but we've got to work out how to do that from a security perspective. As I said before, and this is sort of one of the most glib things to say, the word tritium might not mean anything to those in the room not on fusion, right? Who here knew the word tritium before yesterday? Fusion people, put your hands down. But if you speak to a Japanese person and you ask them what is tritium, a lot of them are going to say, oh, I know what that is. That's the really dangerous stuff in Fukushima. Because there are 2 grams, just 2 grams, in the water waste inventory of Fukushima, and it has been a major political challenge to work out what to do with that. So I'll leave that at that. But the final thing I'll say is a sort of a company piece is that the plant that I mentioned yesterday, Unity 2, that we're building in Canada, we are building the fuel cycle system similar to what Susanna showed in the Aspen diagram there. We are going to be putting tritium in the system. We know how to handle it. We're designing the system to be safe. We're working out everything from monitors to pumps, systems that we can then take apart and work out how much tritium's left in there, so on and so forth. That will inform regulation. It will inform leak limits, emissions targets, which materials you can and can't use, and so on and so forth. So we want to be able to collaborate on international tritium standards to help understand how we can regulate tritium as a problem that can be certainly managed easily, I think. So real but solvable is, I guess, my message. So I'll stop it there. Thank you.
Thank you. Thank you, Richard.